Well, hello, I'm David, I'm the coordinator of the Maths Learning Centre. It's semester 2, 2022, and this is a revision seminar for real analysis, and it's going to be just a grab bag of different bits and pieces, so I'm not going to give it a title, I'm just going to do things as we go along. Okay. So I've got a problem here that says oh, nope, I was looking at the wrong one. That f and g, which both send r to r, are uniformly continuous. Prove that f of g, which also sends r to r, is also uniformly continuous. Okay, so here's the thing. It would be really important to know what uniformly continuous meant from the context of this course. And it might be good to talk about the difference between ordinary continuous and uniformly continuous. So if I'm right, and I'll guess this, just wait a second. If I'm right, the definition of continuous is being continuous at every point separately. So this is where we're just going to think about the meanings of these words before we actually do the problem. So I think this is the definition. F, which sends some set to R, is continuous at A when for any epsilon greater than 0, there is a delta greater than 0 such that whenever the distance between x and A is less than delta, I'm going to say if, such that if the distance between x and A is less than delta, then the distance between f of x and f of A is less than epsilon. Does that sound right? For the definition of being continuous at a particular point? Feels like it should have an epsilon and a delta in it. Because the picture in my head is saying that there's my function, there's the point A. And if I want to be within this, if I want to be within this distance, that's within epsilon, that's within epsilon of f of A, then there is a delta that I can be within A, and then for all the x's here, all the f's are within that distance. And however small that delta is, however small that epsilon is, there's a new delta that fits all of the function values within that zone. So that's what it is there. But if I wanted to make it even closer, like that, then there'd be a new delta that goes with that fits all of the function values within that plus or minus epsilon zone. That's delta this way, delta that way. And so however close you want to be, you can get close to A, and the function is always definitely that close for all of the zones in there. And there are a couple of alternative definitions that probably were mentioned later about open sets and that sort of thing, and sequences and stuff. But this is the original recipe definition, as far as I'm aware. So that's what it means to be continuous at a specific point. That's my understanding of that. And if I wanted to prove it was continuous at a specific point, then I would need to suppose there was an epsilon greater than, let epsilon be greater than 0, because it's a 4NE, and so you've got to say, well, let epsilon be greater than 0, you have to use algebra in the high school sense of give a name to the unknown epsilon, because it has to work for all the epsilons. And then you have to convince the reader that and yourself that there is a delta that goes with that epsilon. And so you have to tell them what the delta is, or convince them that it really exists. And then also simultaneously show them that whenever x is closer than delta to A, then f of A x is closer than epsilon to f of A. And so the structure of the proof will go, let epsilon be greater than 0. Somewhere it will say, suppose the distance between x and A is less than delta. They'll be working in here, and it will conclude with a therefore there. And before you conclude that x minus A is less than delta, before you start by supposing that x minus A is less than delta, you have to tell the reader what delta is and convince them that it really exists. That's sort of how the proof will go to prove that it's continuous at a specific point. So if you want it to be continuous just without mentioning a specific point, that means it's continuous everywhere. Definition, f which sends the set A to R is continuous with no particular reference to where it's continuous when f is continuous at each A in the domain. And so to prove it's continuous, you say let A be a point in the domain, and then you do the proof for being continuous at the point A, but the A is now unknown. It shouldn't be all that different. It should be okay. So that's what it means to be continuous. And it's really important to notice that being continuous at a point A means that each specific point A will have its, once you've picked an epsilon, each specific point A will have its own separate delta, and there might be different deltas to go with each epsilon at different A's. So it might be easier to get close to f of 5 than it is to get close to f of 7, for example. So there are some functions, so functions that shoot upwards. I want to point something out here. This function, like 1 on x, for example, if you want to be within like that epsilon of this point, then your delta is like this, could be this wide. But if you wanted to be within that same epsilon of this point, then your delta has to be only this wide. And if you want to be between that epsilon of this point, then your delta has to be only this wide. So this function, it's harder to get close to the function value when you're closer to x equals 0. And so this one is quite a relaxed size delta. It's all very luxurious. I can use as much space as I want. And this one, it's a little less. This one's more stringent. And so the delta is different at different, for a specific epsilon, the delta you need to get within epsilon of the function value is less and less as you get closer to 0 for this function. And that tends to happen for functions that are that have an essential discontinuity here, that have a limit going to infinity. At this spot, it tends to happen that way. Pretty sure there's a proof that says if a function's bounded, then it's fine. So just pointing that out, that at different a's for the same epsilon, you'll need different deltas, usually. The phrase uniformly continuous means that at different a's for the same epsilon, you don't need different deltas. You can do it all with the same delta at every a. Pick a specific epsilon, and it doesn't matter which a you're at, you'll get the same, you'll be able to use, there will be a delta that will work for all of the a's. So the definition, f which sends a to r is uniformly continuous when, for any epsilon greater than 0 and any a in a, there is a delta greater than 0 such, so just say, wait. For any epsilon greater than 0, there is a delta greater than 0 such that if the distance between x and a is less than delta, then the distance between f of x and f of a is less than epsilon for all a in a. So the difference is, for this to be continuous at each a, you choose the a, and then for any epsilon greater than 0, there's a delta that goes with that a. Whereas this is saying you choose the epsilon and then you choose the delta, and it has to work for all the a's simultaneously. That's the difference. But the bit where you do this part of the proof will look the same, because you're still going to start with x minus a is less than delta and prove that f of x minus f of a is less than epsilon. That's still true. That part of the proof will look almost identical. It'll just be the choice of what delta is will be different. And so it's useful to know that this delta can technically use the number a to figure out what delta is. So to compare them, for ordinary continuous, you can use a to define delta. But for uniform continuous, you can't use a to define delta, because it has to work for all the a's, so you can't have a different delta for different a's. That's one of the main differences between the proofs. All right. How are you feeling about everything I said there? Yeah? I just have to talk it out to myself just to make sure I get it. I only get to do this once a year, compared to Maths 1B, which happens 3 times a year, so I'm really good at that. Okay. So, I think we can try and do the proof now. Apologies to Raymond. This is your question, and it now has a video about it, but whatever. I'm sure this exists on the internet already. Like, it's not like real analysis is new. It's been around for about 100 years. When were Bourbaki working? Between the world wars, I think. So not, about 100 years. Okay, so so we have f and g, which sends the entire of r to the entire of r, be uniformly continuous. And so we know that f of g of x is f of g of x. We know this to be true. That's what this symbol means. Ooh, interesting. So I'm just interesting. So to show that it's uniformly continuous, we would have to say, let epsilon be greater than 0. And then somewhere here, I have to tell the reader what delta is. Somewhere here. And then a little further down, so in here I have to say what delta is, somewhere in here, that's what I'm thinking. And then I'm going to say, suppose the distance, and also after that I'm going to let A be a point in R, because that's what the domain is. And then I'm going to suppose that the distance between x and A is less than delta. And then there'll be some working, and I'll conclude at the end somewhere that the distance between f of x and f of A is less than epsilon. That's what the proof ought to look like, based on the definition. So the definition has a for any epsilon, so that means that the proof, it normally looks like a let epsilon. There is a delta, which means I have to say what delta is, and then it says for any A in the domain, so I have to say let A be in the domain, and then it says if then, and so in a proof, an if then is usually a suppose blah 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 therefore. Right, so this is the shape that the proof will take. It may take more space than I've given it. So this bit here we'll have to fill in, and this bit here we'll have to fill in. Okay. All right. And I may have to completely change my entire plan and do a contrapositive or contradiction or something, but this is the original plan. Okay. So somehow I have to think about how this is going to work here, so that when I choose the right delta, so that when I do this working, it works out. So usually when you do these proofs, you attempt to do this bit. So I'm going to think about that's not f, we want f of g, don't we? Damn it. Already noticed a problem. F is the wrong function. The function I'm supposed to be talking about is f of g of x minus f of g of a. That's better. That's the thing that the proof was actually about. It's good. Good to remember that know that I'm proving the right thing. Always bad to get to the end of a proof and realize you've proved something different to what they asked. You'd still get some marks in an exam for doing something useful. Exam markers are trying to give you marks. The assignment markers are not always the same. They're trying to make you learn things, and so sometimes they deliberately take marks off so that you notice stuff. But exams, it's too late to notice anything, and so they'll try and just give you marks, if they can. Right, so let me just think about what f of g... I'm going to draw a picture because that's my first instinct always, is to draw a picture. So here's x's, and there's my point A. And then here is what g of x is going to come out to. And so it would produce a number like this maybe. And then here's what f of g of x would come out to, and it might produce a number like this here. So this would be g of a, and this would be f of g of a, like that. And so I would like to pick a delta here, like that, so that no matter what all of these points come to, and no matter what all these points come to, all of the answers here fit within epsilon, like that. That's what's going on. And this is the only way I have of understanding how not the only, but this is the easiest way for me to understand how a composite function works. Instead of thinking of it like a graph, think of it like a dynagraph, where moving along here moves the answer along here, And then inputting these answers into F moves these answers along here. And it may be that these are in the reverse order. It may be that when I move along here, F goes this way like that multiple times. It doesn't really matter, but the idea is that this zone ends up with this zone and this zone ends up on this zone. So it seems to me that we've actually got like a second level delta just here. That there will be a delta, that if I'm within that, it's not the right delta, but there will be a delta dash, so that when I'm within this delta, then f of g of x falls within this epsilon, and then there'll be a delta that makes g of thing fall into that delta dash. And link them together. So I'm even going to call it delta dash, because do you know what, that's going to freak me out. I shall call it gamma, because otherwise my dashes will get lost in my writing. So, okay, so I know that since G is uniformly continuous, there is a gamma such that whenever you're within gamma of G of A, F of G of A is within epsilon of thing. So this is what I'm going to say now. I can actually do my proof. And so it's going to take a while for me to fill this in, but this is going to be proof piece number 1. And so here we go. Proof piece number 1 says that since F is uniformly continuous, there is a gamma greater than 0 such that if x, the distance between x and g of a is less than gamma, then the distance between f of x and f of g of a is less than epsilon for all a in R. So that's the definition of uniformly continuous for f, but with the point I'm interested in being g of a. So I'm thinking about uniform continuity just on this piece of the picture. The center is g of a, and so that's what I put in the spot where a normally is. So it's actually technically for all g of a in R, like that. Oh, wait, just a second. Can I be even more specific? For all b in R, and in particular, it also works for g of a, no matter what a is. I just want to be as general as possible to begin with. Okay. So this is definitely the truth for f because it's uniformly continuous. So I have now declared the existence of the number gamma. Right. And now, since G is uniformly continuous, gamma can now play the role of epsilon on this half of the picture. Since G is uniformly continuous, there is a delta greater than 0 such that if the distance between x and a is less than delta, then the distance between g of x and g of a is less than gamma for all a in R. Okay, sweet. And that's the delta I'm going to pick, the one that I borrowed from G. So in this particular story, I don't have to say exactly what delta is, I just have to say there is one, and the one I pick is that one that exists. So now I have declared the meaning of the delta that I want. And so now I'm going to go direct from here to here, which is what I'm trying to do. So now I'm going to say suppose, so let A be something in R, and suppose that the distance between x and A is less than delta. And this is going to be my proof part number 2. So I've just said suppose x minus A is less than delta. And so therefore, the distance between g of x and g of A is less than gamma. And therefore, the distance between f of... oh, that's interesting. I really thought I had it. That's okay. Yep, that'll work. This is playing the role that x plays in this story here, and this is the playing the role that g of A plays in this role here, and so it's okay. I can follow the proof. It'll be okay. Which is what I wanted. And so this was the only 2 lines in that second bit. Cool. And so therefore, f of g is uniformly continuous. I just want to deal with my uncomfortable feeling for a second. So we know that whenever x minus g of A is less than, whenever x is within gamma of g of A, then f of x is this. But if x happens to be g of x, it'll still work. Okay. Yep. So if I really wanted to be absolutely certain to myself, I can just put in here, I know that when y minus g of A is less than gamma, then the distance between f of y minus f of g of A is less than epsilon, and then let y be g of x, and then it works. Yep, okay, cool. That works. That makes me feel better. I'm okay with not putting it in now, but I could put that bit of working in that line just there, just to be completely sure. Because it doesn't really matter what the letter is, but just making sure. Right. How do people feel about that proof? How do you, which move did I do in the act of coming up with the proof that you think would be the thing you could borrow for future proofs? Yeah, I like it. Yeah. So I don't know if anyone came to the Ready for Real Analysis thing or watched it right at the beginning of the semester. And I talked about one of these models for how functions work. And I suddenly remembered I was going to draw a picture with a graph and went, just a second, I remember that I can think of functions as moving from one axis to another instead of thinking of them as a graph. Yeah. Kind of looks like a torch shining light. Yeah. Yes. Second coming. Yeah. Light from above. But a torch is probably better. Very physics, you know, like the diffusion thing with the photons going through the little holes. My memory of physics is pretty vague, but I have a very strong memory of shining a strong light at a thing with slits in it. Okay. Right. So the thing is that one of the key skills you need for a real analysis exam is coming up with a proof in a short amount of time. And so I've done a few things to help me make sense of it. And yeah, the picture was what made me figure out how I was going to do that proof. Now, I think that the people who mark the real analysis exam will probably be okay with you actually doing exactly this and just saying, for this section of the proof, see this page if you want. But that's one of the things that scribble paper is for. Yeah. And so it turned out that the first bit was longer than the second bit, but I didn't know that at the beginning. Okay. I just want to say one more thing about this. This theorem works perfectly well if it's just straight up continuous. And the theorem that will actually look almost exactly the same, the proof will look nearly the same, except for you will let the A be an R before you choose the delta. Yeah. But you'll still make the exact same argument. For this specific A, there is a delta that works. And if there is a gamma that works, and for this specific G of A, there's a gamma that works, and for this specific A, there's a delta that works, and so it'll work. It's just that you chose the A first. Whereas in this proof, you choose the A after you've chosen the delta because there's a delta that works for all the A simultaneously from the other functions. But the proof will look almost identical, except for this line will be here instead of here. Yeah. And it's because it's uniformly continuous to begin with, so that deals with all of the problems you have with uniform continuity because the original functions were uniformly continuous. So I just want to point that out. Sometimes the proofs look very similar, except with one line in a different spot. Yeah. I only saw that because I saw it on your thing. There was a note in the lecture notes that said the composition of two continuous functions when it's defined is also continuous. So. Okay. Just thinking about where I'm going to go next. Well, let's just another problem. Let's see what happens. At f and g, which send the interval from a to b to r, the functions not necessarily continuous, such that g is integrable. Oh, not just g is integrable, okay. G is integrable, and the integral of from a to b of g is 0, and 0 is less than or equal to f of x, which is less than or equal to g of x. For all x in AB. What the hell? How can the integral of g be 0 if g is always positive? Wouldn't that mean that g would have to be 0? Wouldn't it? Surely. I mean, it might have some points that are negative, but just don't contribute to the integral. No, it says that they're all positive. Why does this... What? I just want to... crap, there's supposed to be a dx there, isn't there? Oh no, nope. This is a new notation for me. I am not comfortable. Okay. All right, that's okay. I prefer there to be dx's, but I get why people don't. It freaks me out. All right, so because you shouldn't turn off your ability to picture things just because you're doing maths, just because you're doing calculus. Sometimes, like, even though calculus was invented to try to figure things out about functions without drawing them, it doesn't mean you shouldn't still attempt to draw them. Like, you can figure out where the maximum of something is by differentiating it and making it equal 0 and subbing it in, and you don't have to draw the function to find its maximum. You can use the information from the derivatives to do it. But it's all based on knowing that there was a picture there somewhere, even if you didn't draw it. So this information here says to me this information here. There's A and there's B, and G is positive and F is always below G. Something like that. That's what that says to me. But this information here would seem to suggest to me that G would have to be always 0. Like, if the area, if G was ever not 0, right? So if this was like G of the number C and it wasn't 0, the integral would have to be, and for the integral to work out to be 0, I couldn't have something like that, because that would not be 0, the area, right? So the only way that G could have a function value that wasn't 0 would be for it to just be sitting there all on its own, not with anything around it. It would have to be more like but the rest of G is 0, something like that. Because that could totally happen, right? Because they said that G might not be continuous. And I think this is why this warrants a proof. Yeah. Yeah, okay. I just wanted to cope with that, because if G was if G was always 0, we would have to prove that G was always 0. Okay. So this is hinting to me at what the proof needs us to do. It needs to tell us, somehow indicate, I'm not 100% sure what's going on yet, but somehow indicate that the only way for G of x, for f of x to not be 0 is for it to just be a standalone number that doesn't make a difference to the overall integral. I'm not 100% sure how to go about doing that yet. Okay. So that's fine. This is my understanding of the proof. And if I were in an exam and I was still blocked, not knowing what to do, I would write down that reasoning. I would say, I'm not sure of the formal proof yet, but these are my thoughts. So that the person reading your exam knew that you had thoughts and you understood what the definitions meant. Right. But if you're a real mathematician doing real mathematics and proving stuff, you would just have these notes somewhere and go, I'm just going to put this away for 3 months and come back to it later. That's how real maths works. in a seminar yesterday with the careers service, and they were saying, guess what the formula is for career success. And the people at my table are all stressed out and going, we can't think of that. And I said, so cut yourself some slack. Mathematicians take centuries to come up with formulas. Just, you've got 5 minutes, just put whatever you want on the page. No one cares. Yeah. But in an exam, someone cares, but you'll still sometimes put whatever you want on the page so that there is something there. Success in real analysis and pure maths generally is like that. Okay, so I do need to know what it means to be integrable, which presumably means that one can calculate the integral. I think that's what the definition means. I'm not sure. You might want to look it up for me. And I am going to have to actually calculate the integral just here. And so therefore I need to know how one formally defines the value of a definite integral. And I'm pretty sure it's the, I'm pretty sure it is something with upper sums and lower sums. So I'm pretty sure, what is an integral? That's something that I want to know. What is that for a random function? And I'm pretty sure it's the supremum of all the lower sums and the infimum of all the upper sums. Yep. So we'll get the upper sum of f on a partition P, and we'll do the infimum of all of those given that P is a partition. And we've got the supremum of all the lower sums of f of P given that P is a partition. And if those two numbers are the same, then it's integrable, and whatever the number that they both are is the integral. Is that the definition? Yeah. So if they're the same, it's integrable, and the number is a to b of f. Okay. And this thing is defined, just to be absolutely sure I know what's going on. This thing here is saying that you cut your thing into a partition, not necessarily, like in Maths 1A, they all had to be the same width, but here in real analysis they don't. And your function does whatever it does, and you take the supremum of the function value on each of these and multiply them by the width of the gap in the partition, and you get the answer. Yep. Cool. And I very carefully said supremum and not maximum, because your function might not have a maximum on that interval, but to be integrable, it does have to have a maximum on every, a supremum on every interval. And most functions are continuous anyway, and so they're actually bounded on a finite interval, so that's nice. Okay, so UFP is the sum of the supremum of f of x such that x is in the gap times the gap itself, the width of the gap, something like that. That's my not a very good mathematical way of saying it, but I can make it clearer if I need to. It was the sum of the width of the gap times the supremum of the function value of x such that x is in the gap across all the gaps. Yeah. And officially, a partition is a list of x's, right? It's not a list of intervals, it's just a list of different values for x that are the edges of the intervals. So the official meaning of the P is just these numbers that define the gaps between them. So, yes. P is just the list of x0 up to xn, which is the dividing lines between the intervals. The official word's probably subinterval, whatever. Okay. So the reason they do this is makes it easier to talk about refining partitions, because you can include just extra x's and then you've got a new set of endpoints. And so if you have two partitions, you can create a partition that just has all of the edges from both of them, and then that causes a partition where all of the intervals that you've made, little intervals, are contained within the intervals of the other ones. So a refinement of a partition is a partition that contains all of the same endpoints as this one and possibly some extra ones. Just while we're at it, this is not necessarily relevant, but of P is P union some other x's. That's my understanding of what a refinement is. And so what that means is that the intervals that P creates are the unions of intervals that belong to the refinement. So just as an example, if P is like, 1, 2, 3, 5, 20, then Q being 1, but also it has to have the same endpoints, I believe. Some other x's between x0 and xn. Yeah, okay. You can't go further out. So this might be 1.5, 2, 3, 4, 5, 15, 17, 20, something like that. So it's still got the same numbers it had before, and just some extra ones possibly in between. So Q is a refinement of P. And making it the list of numbers just makes it easier to talk about how to make a refinement. Because in your head, partition probably means the list of intervals, but yeah. And so you'll see the intervals that this one creates, there's two intervals, one from 1 to 1.5 and another one from 1.5 to 2, and those two intervals together make this interval here. So I'm pretty sure there's a theorem that says that if you do a refinement, then the upper sum can only decrease and the lower sum can only increase. They might stay the same, but they can't get bigger. So I think there's a theorem. So there's a theorem that says that for a probably continuous function, maybe integrable, maybe every function, I'm not sure, that if Q is a refinement of P, then the upper sum of the upper sum of the function on Q can only be smaller than the one on P. And the lower sum of the function on Q can only be bigger than the one for P. That sounds right to me, because here's P. I'm just going to call them P0 and P1, and then there's some extra Q's in the middle. And so the idea is that your function, I really should have made it more extreme than that, so it's easier to see what's going on. So that's the upper sum for P. Oh, crap. That's the upper sum for P. And the upper sum for Q and that area we've lost a bit because there's one in between. Yeah. And so the upper sum for Q is the same for these ones, but it's just a little bit less for these ones. So every time you refine it, the upper sum will get a little bit smaller and the lower sum will get a little bit bigger, and they'll tend to approach each other. Okay, cool. Just wanted to make sure I had the vibe of all of this stuff. Okay. So if G, so we would like to show that the integral of f is 0, which means we need to show that the infimum of all of the upper sums is 0. Which means we need to show that no matter how close to 0 we need to be, there has to be a partition that puts my upper sum that close to 0. Because if there was a gap, if there was like an epsilon and I couldn't make the upper sum less than an epsilon, then the infimum would be epsilon and not 0. So I have to get my upper sum total to get down to 0 somehow. Okay? So the thing in my head, which is not going to work in the proof, but the thing in my head is that there can't be uncountably many places where G is not 0. And since if there are only finitely many, I would use them as my endpoints for my intervals. Yeah. Because then when I refined the gap, the height of that rectangle would get narrower and narrower and it would be good. Wow. Still trying to figure this one out. I don't like to resort to looking up to here's one we prepared earlier, and so we'll figure it out for a bit. And if anyone's got any thoughts that are not based on having seen the proof before, even if they are, then feel free to just let me know. But I can see why this problem was hard. Yeah?
I have a basic idea.
Mm-hmm.
So what we can do is we can take the sort of G and represent that as the premium of G multiplied by some root.
Mm-hmm.
Do all that. We know F is always less than or equal to it, so we can say that that upper sum has to be at least as big as, not the wrong way around.
No, that's okay. I think I've got it, and I'm going to write some of the things you wrote down, and then I might ask you for some more input.
Okay.
But I'm not going to get very far without writing it down. I have vivid memories of my year 11 maths teacher doing mathematical induction and me reading out one line of the proof to her across the room, and her, without writing it down, telling me the next line, going, how do you do that? Yeah, she obviously had a very clear visual picture of things in her head. I cannot do that. I did not aspire to learn that skill either. So for this proof, actually, I just want to say something. You're telling me that given if f of x is less than g of x, then the upper sum for f on P would have to be less than or equal to the upper sum for G on P for any specific partition.
Yep, that's it.
So given a specific So given a specific partition P, the upper sum for f would have to be less than or equal to the upper sum for g, which makes sense to me, like all the function values are less, and so the supremum of all of them would have to be less as well, or equal. Yeah? This is totally a theorem, I'm sure, or a lemma at least, or an unspecified proposition that no one decided whether it was important enough to be a theorem or not, and so they just kept it being called proposition. Okay. I think we're just going to believe this is the truth, but it makes sense to me. Because if you pick one of the intervals involved in the partition, so on the interval from like xi to xj, every f of x has a g of x that's greater than or equal to it, and so the supremum has to be, just a second. So if x is in there, then f of x is less than or equal to g of x, right? Nah, you would have done a supremum proof at some point to say that if every x is less than a b in the other b, then it has to be less than or equal to the supremum of, yes, that's it, which is less than or equal to the supremum of the values of g of x for g in the interval. Yeah. So if x is in here, this is the interval, that interval is called I, then f of x is less than or equal to g of x, and g of x is less than or equal to the supremum of all the g of x's, because their supremum is an upper bound, and so therefore f of x is less than or equal to the supremum of all the g of x's, and so that is an upper bound for f, for all the f of x's. And so since this is an upper bound, so the supremum of the g of x's such that x is in the interval is an upper bound for the set of f of x's such that x is in the interval, and therefore this set is bounded because it has an upper bound, and this set, and this is one of the upper bounds, and the supremum is the smallest upper bound, so it must be less than that upper bound. And so since the supremum of this set is the lowest upper bound, yes, the supremum of f of x such that x is in I is less than or equal to the supremum of g of x such that x is in I. Yay! Yay, that was a little upper bound proof. I love it. It's so cool. I love upper bound proofs. I mean, I hate them while I'm doing them, but when I'm finished, I'm really proud. So, yeah, that's so fun. That's one of my favorite arguments, to go, well, this is an upper bound, and the supremum is the smallest of them, so it must be less than that. Yeah. Okay, and so on every interval, the supremum of the f's is less than or equal to the supremum of the g's, and so therefore the sum of the supremum of the f's must be less than or equal to the sum of the supremum of the g's. Well, and you multiply them all by the same things anyway, and so it's okay. Yes. So that was just me trying to prove it. So the finishing thing is, so therefore that, you know, x, this is xi plus 1, xi plus 1 minus xi times the supremum of f of x such that x is in the interval is less than or equal to xi plus 1 minus xi times the supremum of the thing. And therefore the sum of all of these things has to be less than or equal to the sum of all of these things. And so therefore u of fp has to be less than or equal to u of gp. Ah, that's so satisfying. I wish you could just write squiggles in exams. It would be much easier, but you can't. So, but again, if you didn't have time, and in the last 2 minutes you suddenly thought of this proof, and that was all you could write, it would be better than nothing. So, I always tell people to stay all the way to the end. In Integration and Analysis 3, there was one question I couldn't do, and in the last 5 minutes I suddenly had an inspiration. I scrolled it all down. I got 100% on that exam, so there you go. As I said in the revision seminar yesterday, you know, like with super funds, past performance is not indication of future performance, but, you know. Okay, so where were we? So you were saying that since we can believe this truth here, we know that given any epsilon greater than 0, I think we've got a proof now. So in order to show that damn it, where'd they go? In order to show that the integral of f is 0, we have to show that both of these things are equal to 0. Which means we have to show that this gets as close to 0 as you can get, or that one of them actually is 0. So since we don't know for sure that one of them is 0, we have to show that we can get as close to 0 as we can get. And so we can borrow from G to tell us what to do for F. So we can now say that since the integral from a to b of g of x dx is 0, the infimum of the upper sums of g such that p is a partition of AB is 0, because the integral is this number. And so therefore, so suppose epsilon is greater than 0, then there is a partition P such that u of GP is less than epsilon, since the infimum is 0. Since the infimum of these objects is 0, if I want to be this close to 0, it's possible to get that close. Now, I do want to say, if this had been 10 here, it would have been 10 plus epsilon here. Yeah, because I'm imagining that this is my possible upper sums. And so here is 0, and there is one in this zone, and no matter which epsilon I pick, there's one in this zone, so I can get as close to 0 as I want. So these are my areas. Okay, sweet. But we know that u of fp is less than or equal to u of gp, which is less than epsilon. And that's what you were heading for. Yes, thank you. And so, therefore, there is an f within that zone. And so, therefore, the infimum of the set of fp's such that P is a partition of AB must also be 0. Yep. Because I can get as close to 0 as I want. And I guess, possibly less than or equal to 0, you'd have to show it can't be negative, I guess. Damn.
Are we talking the question that f is integrable?
No.
Yeah, in that case we have to do the whole one and lower sum.
Yeah. So I have to do this whole thing again with lower sums as well, because the definition of being integrable is that both of those things exist and they're equal to each other. I'm just going to say less than or equal to 0. And then, again, 0 must be the supremum of the lower sums of GP such that P is a partition of AB. And if we suppose there's an epsilon greater than 0, then there is a partition P such that the lower sum of G and P is greater than or equal to minus epsilon. So this time I'm approaching 0 from below. Like that. It may be that all the lower sums are 0. And in fact, I expect them all to be 0 actually. But it doesn't matter, I don't care. Like, it's irrelevant for this story. Yeah, actually, I think all the lower sums are 0. But it doesn't matter, the argument still works. Anyway, and so we've got, but L of FP is greater than or equal to L of GP. No, that's not going to work. Does this work? No, it doesn't work. It doesn't work. I don't think this is going to work because this only works if F is greater than or equal to G, which it's not. Crap ass. This particular argument doesn't work. We have to do something else. I think we have to show that the minimum is 0. Like that there is a partition where the area is 0. Where the lower, yeah. Yeah. Because the information we have is that 0 is less than or equal to F, which is less than or equal to G. What were you going to do?
I'm actually thinking about what you said, because I think that could be a good way to go. The way I had it, at least rather than using epsilons for the previous one, I just had the infimum of both of the upper sums had to maintain that inequality. So I think for this, showed that there was some inequality between the supremums of the lower sums. So presumably the supremum of L of F is less than or equal to the supremum of L of G. And that might make it easier.
Wait. I've got it. Or do I? Right, so it's like, well, F is more than 0, right? So in the same way that so the same argument we did for the upper sums should tell me that if F is less than or equal to G, then infimum of one should be less than or equal to the infimum of the other by the similar argument, but backwards, right? So the L of f of p should be less than or equal to L as well?
L of f of p should be less than or equal to L of g
As well.
as well.
And in particular, L of 0p should be less than or equal to L of 0 of fp.
Yes.
And since the L is definitely less than or equal to the u for every u, like the supremum of all the L's has to be less than or equal to the no, whether they're integral or not. Like all of the lower sums are less than all of the upper sums. Just let's stop feeling a bit stressed out about this. I just need to stop and let myself deal with that feeling. I was okay with this. This was okay. I understood this bit of the argument because I believed that this was definitely true. I just want to be sure in myself since f is more than 0, the upper sums for f of p must be more than the upper sum of 0 for p, and the upper sum of 0 for p is 0. Like the function that's always 0, its upper sum is 0, and its lower sum is 0 on every possible interval. So it's definitely true that that is the truth. So since 0 is less than or equal to f of x, it's less than or equal to g of x, this is true. Like this bit here is true, and therefore this is true. Yes. So it'd probably be better to write them on separate lines, but that's okay. And so therefore the infimum is in fact 0.
I don't think we know that.
No, we do. Because we can get as close to 0 as we want, and they're all positive numbers. They can't be negative, and they have to be less than every positive number, which means they are 0. Yes! The infimum is the biggest lower bound, and 0 is one of the lower bounds. Yep. And so the infimum has to be greater than or equal to 0 because of this fact here, and the infimum has to be less than or equal to every epsilon because of this fact here, and so therefore it's equal to 0. Yes. Since UFP, there exists a UFP that's less than epsilon, and all UFPs are greater than or equal to 0 for all epsilon, something like that. That's the reason why the infimum is equal to 0. Not that that proves the integrability of it. We need to show that the lower sum, the supremum of the lower sums is also 0. But that does seem to me to say that since f of x is greater than or equal to 0, then that would mean that the infimum of f of x on any interval will be greater than or equal to 0. For any interval I. And that would mean that the sum of the infimum for f of x on any set of intervals will be greater than or equal to 0. Yep. And therefore, the infimum, no, not the u. This would be the lower sum. Sorry, the infimum. Therefore, the supremum of the L's has to be greater than or equal to 0 as well. Yep. Because the supremum is greater than all of these numbers, and they're greater than or equal to all of these numbers, and they're all greater than 0. Yep, doing well. And since the supremum, since all of the lower sums are less than or equal to all of the upper sums, and the infimum for the upper sums is 0, this supremum has to be 0. But the supremum of LFP, P is a partition, is less than or equal to the infimum of the U's, P is a partition, which is 0. Therefore, the supremum of LFP, such that P is a partition, is also 0. And so therefore the supremum of the lower sums is the same as the supremum of the upper sums, which means it's integral, and the answer for both of those numbers is 0, which means the integral is 0. Therefore, f is integrable, and the integral from a to b of f is 0. Wow, I'm sure there was probably a slightly easier way to do that, but I feel good about it. I reckon there's a theorem for lower sums similarly to the one that I was using for upper sums that could have just done this a little more directly. And I'm pretty sure it's true that for any function whatsoever, UFP is greater than for any partition P and Q. Less than, sorry. Pretty sure that's true. Yep. And I think you prove it by combining P and Q into a refinement and saying that it's definitely true if you've got the same partition, but we were using the same partition anyway, so it's okay. But it's definitely true if you've got the same partition in both of these spots, because the L is made as the infimum of some numbers and the U is made as the supremum of some numbers, and so the infimum's got to be less than the supremum for the same set of things. And what you can do is you can make a refinement of both of them, which is basically the union of P and Q, and you know that the lower sum of that refinement is less than or equal, the lower sum here is less than or equal to the refinements one, it only gets bigger, and the refinements between them. Yeah. So let R to be P union Q, which is a refinement of both P and Q. And then L, F, R, F, P is less than or equal to L, F, R, because when you refine it, the lower sum can only get bigger. And U, F, R is less than or equal to U, F, Q. Whoops, sorry. Because when you refine it, the lower upper sum can only get smaller. And so since this number, and LFR is less than or equal to UFR, so you get LFP is less than or equal to LFR, which is less than or equal to UFR, which is less than or equal to UFQ. Yay. Proof. Yes. Yay! Using the fact that refinements do this thing. Which I'm sure has to be proved separately somewhere. Like real analysis is the most connections between proofs-ish of the pure courses. Like algebra had a few pieces that were all separate to each other, algebra 2 as a pure course, that sort of didn't feed into each other, but the whole of real analysis, every bit of it feeds into another bit of it. You know, Ray got you to do those diagrams with the arrows. Yeah, and like everything, there is a bottom somewhere, but the bottom is the axioms of the real numbers and the definitions of what the words mean. Yeah, that's so cool. Real analysis is cool. After you've done the exam, you can appreciate the coolness of it. The exam makes it less cool. Similar to, you know, I studied some Shakespeare in Year 12 in English, and it was significantly less cool having to do an exam on it. But afterwards, it became cooler again. Okay. So, can I ask a question? I've done this whole thing. This thing here, it feels like, since I kept mentioning that thing, that it should have a name. Is this called like the upper integral or something? Like, does it have a name or a notation for this object?
Yeah, just LF without.
It's just called LF.
It's just called LF, like the lower sum.
Right, so this is the lower sum. So if my entire proof could have skipped quite a lot of the symbols by writing LF for this every time.
Yes.
And UF. Okay, just a second. This thing is called LF. Right. Cool.
Oh, sorry, like L bracket F.
L brackets F. Okay. The reason I ask is anything that when you do a proof you have to write many times probably would be better if you gave it a name. Or probably someone's already given it a name. Right. And so being integrable is now saying that UF is equal to LF. Yep. And they both exist. So. Right. Cool. A lot happened there. So what happened there was that we had part of the problem-solving process was us trying to understand why this was even a problem and thinking about what would cause it to be not true, possibly. Like what would cause the integral of a function to be 0 without the function itself always being 0. That was a useful thing to think about. Even though it didn't come into the proof, it was still important to think about. And then we also had to think about everything we knew to be true about integrals and the definitions of integrals for functions that are less than or equal to each other. So we had a thing here that we did use, this. This is our truth here. And there were like 3 or 4 or 5 different facts about upper sums and lower sums that we used to make sense of our proof. So we had to know all of them and have them ready for us. And they're all connected together when we actually finally got to our proof, which was here. And in the end turned out to be basically a page, possibly shorter if I had used the correct notation for this thing. So So my recommendation as you work through things before your exam comes, and my recommendation if you're in the future watching this before the end of real analysis, but if you talk to students who are going to be doing this course next year, recommendation is every time you do any problem, take note of the things you use to make it work. And go, well, those are things I have to know because I have to be able to use them when I need them. Yeah. So there's a summary that you could make of facts that are true about upper and lower sums, regardless of whether the integral actually exists or not. They are useful facts to know about. And also facts that are true about infimums and supremums and that sort of thing. I refuse the plurals infima and suprema because I just refuse. But I also call them octopuses and axes. I'm in a good mood, I will say axes. Sometimes I even say matrices. Yeah. Okay, wow. Where are we? 1:45. Does anyone want to talk about anything in particular? Okay, I'm going to pause the recording for just... That's all right. So I'm just going to... I was asked about the extreme value theorem. Sorry? I did. Thanks for checking. The extreme value theorem says, and I'm going to try and remember it from what I just looked before and then check if I was right. So if f, which sends the function, if f is a continuous function, real valued function, then if it's defined on a compact set, then it has a maximum and a minimum. So if f, which sends k to R, is a continuous function on K a non-empty compact subset of R, then F has a maximum and a minimum. Okay. So there are some words here. Compact means closed and bounded. Is that right? I have a feeling that's not the definition of compact, but it is the truth. So it'll be okay. The definition of compact is what? All the sequences converge to something that's in it? Or is it something else? All right. All right. So I'm just going to leave it with that, and I'm not going to say it's defined to be, I'm just going to say that's what it means. In the same way as over in linear algebra, linearly dependent means that one of them is a linear combination of the others, but that's not the definition of it. And what that means is that basically it will be the union of closed intervals. So it could be a single closed interval, or it could be several closed intervals joined together with gaps in between them, but it doesn't matter, it'll still work. Okay. So it could be like, you know, A, B, union, C, D, union, something like that. And then there'll be a last one somewhere. Okay, cool. That's what compact means. And a maximum is a supremum that's actually in the set. So maximum means, in this context, that f of x is less than or equal to f of a for all x in the set K, and the point A is actually in the set K. So there is a point A in the set K, so that all the other points have a function value less than or equal to that one. And that is what a maximum is. If the set point A wasn't in the set K, that would just be a supremum, not a maximum. So yep. And minimum will be similar, but the other way around. Like it's greater than or equal to the minimum. Right. So back when you first learned about local maximums and minimums, probably in year 11 or 12, a local maximum is a point whose function value is higher than all the points nearby. But an actual maximum is a point whose function value is higher than all the function values everywhere that you're allowed to do the function. Yeah. So really, like here's my interval where it's defined, and my function value does whatever it does. And there, that's the maximum. And just to be absolutely clear, there's the minimum there. So it could happen at one of the endpoints, or it could happen somewhere in the middle. The closed boundedness is basically covering the fact that it could be at one of the endpoints. If it was an open set, you might still have a maximum and minimum, but then again, you might not, because you might not be able to reach this point. That's my feeling about how it works. Don't know how to prove the thing. It seems not unreasonable to me as a thing to be true, but that is what real analysis is for. Like when people invented calculus, they went, oh, this all seems reasonable. And then the mathematicians later got uncomfortable about it and went, oh, maybe I should just fill in some of those technical details just to be sure that things that I think are reasonable are actually true all the time, or at least figure out if the times when it doesn't work, I can sufficiently say, oh, that's just horrible and nasty and we'll never be in that situation. So, yeah, okay. And there's nothing stopping that maximum happening twice or more than once. Or the function just always being the same number and then the maximum is that number everywhere. Okay. So integrals are defined on closed intervals. And so I can imagine that the extreme value theorem comes in some of the proofs to do with integrals, I'd say. I'm just going to repeat that for the recording. If you're on an integral and you're cutting it into those subintervals, since your function is, if you've got a continuous function and it's defined on a closed interval, which is what you do when you do an integral, it must have a maximum on every subinterval and a minimum on every subinterval. So you don't have to worry so much about the infimums and the supremums stuff because it's all just maximums and minimums now, right? But when you define integrability, your function doesn't have to be continuous to be integrable. And that's why you need the infimums and the supremums. Okay. Cool. Yep.
You said before that there are some
Mm-hmm.
So if they say
Well, the only word, hot tips, maybe. I mean, the only ones I said before is like language. I'm just going to collect them together. I know that if it says for every, blah, 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 in the statement that you're trying to prove, then in the proof that usually looks like let. And if it says there exists, in the proof there's no particular words for it, you just have to mention it. Like there exists this thing, and that just means that somewhere in the proof you have to mention what thing is or why it exists. So there's no particular words for that, but you just know it has to happen. And it has to happen before the thing that this thing does. And if you've got an if something, then something else, then in the proof that usually goes suppose thing, blah, 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 therefore thing. They're the only ones off the top of my head I know, and they're the most common, right? And while you can write it differently to that, you can say assume here instead of suppose if you want. But I don't like to say assume because I'm not really assuming it's true. I'm just wondering what would happen if it was true. Because that's what if means, right? If means might happen, might not, but what if it did? And what if means suppose. Yeah. That's my total, really, at the moment, advice for it. I find it really useful for proofs and exams to have a structure for the proof. Because a proof is a sequence of logical statements that are connected together. And so a proof hangs on saying certain things in certain places. And so that's what I find the most useful thing is to go, well, if I know which statements will happen approximately where, I can fill in the bits in between. There is no such thing as good advice that will help you for all possible proofs. But this is the best I've got, and it does help me. And a lot of students appreciate this way of at least narrowing down all the possibilities to just a smaller number. And I'm using these words because that's what turns up when I read other people's proofs. The word let appears all the time. I love the word let in maths. It's one of my favourite words because it's like, oh, the letter A is just waiting. It wants to be something, and today I'm going to let it be. Yeah. So yeah. Anyway, that's the thing I have in my head. Yeah. If I had done some other proofs, I might have come across, read some other today. I might be, I'd be able to pull this off out of my mind. The only other proof advice I have is don't be ashamed or afraid to draw a picture of what you think is happening. And there are many different pictures you could attempt to draw. Don't commit yourself to representing it in one way, because many of the attempting to draw the picture can tell you the problems that will come up in the proof. Like when I attempted to draw this thing, it didn't come up in the proof, but at least it made me wonder why I would need to prove such a thing. Because when we first read this, we went, doesn't that mean that that G itself has to be 0? And then it made me go, oh, okay, so it's more complicated than that. And then that means I wouldn't try to prove that G is 0 because I realize that it doesn't have to be. Yeah. But in some cases, when you attempt to draw the picture, you start to go, actually, the only way is for this to be 0. That's what I'll prove. Yeah. So, yeah. I'm just going to stop there. That's okay.